All right, so I apologize for the lack for the last 2 days. It's been a rough weekend for me. My dog's sick, and then my wife is still working, so it's not the funnest trying to be a single dad during the day and then trying to take care of a dog at night. My wife's working graveyard shift, so it's been pretty rough. So I do apologize, but hopefully for the rest of the week I can get back onto it. So we kind of left off with how current and electrical wire could have a magnetic field, and the main focus today is to kind of explain how motors work. So that's our goal. I'm going to kind of go through a couple of slides to review again. So because I know in the quiz a lot of people are confused because in the video I did it where the polarity was on one side. So the positive, I believe, I can't remember, but on the left side, but on the quiz the positive was on the left. It wasn't meant to kind of trick anybody. I just randomly picked one for the video and it just happened to be the opposite. So I do apologize for that. But like I said, it was only for participation anyway. So hopefully it works out that way. So when we look at this picture, we have a current going in one direction, and then we have a magnetic field that's going to form on this wire. So notice that the wire is moving in this direction right here. So right now, the only way your right hand can kind of emulate that is if, let's say, here's the wire, and I'm going to try to imagine it. So it is going in this direction, I believe, for you guys. So if I'm grabbing it, the current, I believe, has to be going up for you guys as well. So the current has to be going up in order for my right hand rule to work. So notice that on the arrow, on the back side of the arrow, you can't see the magnetic field. So right around here you see a break. Here you actually do see it, so it goes in front, behind, and the only way to do that is if the current was going up. If it was my left hand, notice that my fingers are curling the other way. So here the magnetic field, if I was drawing on the floor, is going in this direction around this wire. So that's once again the right hand rule. Our next one kind of shows the same thing. In this case, the current is going down. So if it's going down, my fingers are going to go wrap around, and notice that it's going to go in the opposite direction this time. So here, the right hand rule, the fingers are going to move in the opposite direction, so in this way. So as a review, right hand rule, thumb is the current, fingers are the direction of magnetic flow. Now, next lecture, I guess what's going to happen is we're going to talk about force, and then that's where you're going to find like the 3-finger rule, but we'll get to that next time. So for now, this will be totally fine. Now, what happens if it's in a loop? And if it's in a loop, you'll notice that the magnetic field is going to change a little bit. So instead of going around it, it still goes around it. Okay, it still goes around it, but you'll notice that it kind of makes a big circle around, and it creates this weird kind of thing that's going on. So if there was a current going around, it's going to look like this. So once again, this is a review. Right hand rule. Here is my current. In this case, it's going from positive all the way down to the negative. So in this case, my right hand is going to grab it. It's going to go in a certain direction. But what I really wanted to show you is here, my thumb is pointing up and my fingers of my right hand is going this way. Okay, sorry, that's a horrible right hand, but you kind of get the picture. On the other side, my thumb is pointing down, and my fingers, let me try to figure out how I would draw this. My fingers now are pointing this way, going this way. So no matter where it is on the loop, the cool thing is, as it goes around, the inside is always going to go a certain direction. The outside is always going to go a certain direction. So no matter where you are on the loop, it's always going to be uniform. The inside is always going to go one direction. Okay, in this case, it's going to go in. So that's when we show the butt of the arrow. On the outside is going to be the tips of the arrow. So it's going to be coming out. Let me kind of make that a little bit better. So butt of the arrow here, tips of the arrows here. And the cool thing is, if you look at this as a whole, this is what happens. So if you look at each individual one, you have this mini little circle going around each individual loop. But when you build it up, you get a nice directional loop this way, this way, this way. And in essence, if this was a bar magnet, north and south, pointing out of the north, going into the south, you're going to get a magnetic field that looks just like a bar magnet, or a permanent magnet is the best way to kind of explain it. So an electromagnet, when you have current going through it in a loop, they're also called solenoids, if I pronounce that correctly. And when you have coils of wire, so that's why when you're in elementary school, hopefully you made electromagnet. You got a piece of nail, you wrapped around a bunch of wire around it, you connected to a battery, and it was able to start picking up stuff. It does it because when you have current going through wire, it creates a magnetic field that looks just like a permanent magnet. So that's the main concept that I wanted to show last time. Well, what's the big deal? Why do we really care about electromagnets? Well, in most cases, even with you guys, it's in a lot of things that you might see. So the most prevalent one are motors. So motors are everywhere. In your cell phones, they kind of help your cell phone vibrate. In your headphones, technically you have electromagnets in there. Usually in class we make both the motor and the headphone, which is a lot of fun. My wife is an MRI tech, so she could take pictures of you using magnets. A lot of us might have wireless charging, which is really neat. And that also has to do with electromagnets that are inside here. Kind of has to deal with more of transformer properties, but we'll get into that as well. But transformers also kind of deals with this. So that's one way that Tesla won over the AC versus DC war, because his system uses transformers, or gets to utilize transformers to kind of transport energy. And we'll get into that again later, but quick thing, the reason why Tesla won is because his system was able to transform lower voltage into high voltage, transfer it really, really far away, use transformers to kind of back it back down to lower voltage back into our homes. So if you ever see like those weird green boxes around homes, if your lights are, or if your electricity is under wire, it's a transformer. If you ever have those overhead wires and you see this trash can looking thing, those are transformers as well. So those are all very important. So these are all applications of electromagnets, from the very simple. This can be both, what's neat about the motor, which we'll kind of end with, this is both a generator and a motor. And headphones kind of, I guess, generate energy, sound energy and stuff like that. So I do want to share with you how a simple motor works. And this is kind of a good video. And we'll kind of skip through kind of the building of it. But the main thing is you have to have a loop of wire. And this is something called enamel wire. So enamel wire is a little bit different from regular wire. Instead of using a rubber insulator, it uses paint, enamel, onto copper wire. And so it looks very, very similar to the wire itself, but it's very, very thin. So this gentleman, or I think it looks like a gentleman, is scraping off the enamel. So now you can have a electrical connection between the two. So he's scraping off the ends. So what he did was he looped the enamel around in a loop, scraped off the ends. So one end is going to be attached to a positive, another end is going to be attached to a negative, and he's going to create the stand that he's going to put on. And with the stand, he's going to connect it to the battery. So here, he's going to kind of tape down the stand. He's going to put a permanent magnet on the bottom after he puts his loop on the loop. So permanent magnet is going to be the bottom. Notice that what's going to happen here. So here is your positive end of your battery. Here's your negative end of your battery. This is going to go all the way into the stand. So right here, this connection right here is a positive connection. Let me change the color for my negative. Here's negative, so this wire is going to go all the way over here through the stand right here. So this connection right here is going to be a negative. So what's going to happen is current is going to go in from one end of the loop, circular around this loop a bunch of times, and come back out. So what's going to happen here is you're going to create an electromagnet. And because of the electromagnet, what can happen is When you put it in, it's going to start spinning. So usually we do make this in class, and it's actually a lot of fun just to make a little simple motor like that. And so a simple motor is nice to kind of explain what's going on. And I'm going to try to do so with some diagrams. There we go. So pretty much this is what the person did. He got this enamel wire or magnet wire, looped it around, and had two ends. So one end of the wire was here, made a bunch of loops, the other end here. What you want to do is scrape off the enamel on only one side. So you'll notice here, the bottom is bare. So that means you could have electrical connection. While on top, no connection. So remember, he put it on a stand. And one end of the stand went to a negative, and the other end of the stand went to a positive. So when it's sitting here, when it's on the bottom side, electrical current can go through, but as it rotates around where, let's say, let me see if I could do this on a PowerPoint. I should have done it. But if it rotated around, the enamel is going to be now touching that stand, so it no longer has electrical current going through. So in one position, it's on. In another position, it is off. And it will make more sense when I kind of try to explain what's going on in my next slide. So what I have here is kind of a diagram of what's going on, but kind of on a side view. So before the loop was this way. So imagine it like, here's my drink coaster, here's a loop. But instead of looking at this way, we're going to look at it as side view. And what's nice about the side view is now I could have a north and a south. So let's just kind of color code it the way it is here. So here's, let's say, the first situation, second situation, third and fourth. Here, remember this is the north and the south end. So let's say if this was always on, north, south, north, south, north, south. So let's say this was on. If this electromagnet was on, what's going to happen is if you have north and south, well, I got it opposite. Dang it. Let me fix it and I'll come right. All right, so hopefully I fixed it this time. I had these two mixed up. So let's start again. Here's 1, 2, 3, 4. Like I said, here's the north, south, north, south, north, south, north, south. I got my order wrong, so I apologize. It'll make more sense once we kind of talk about it. If this magnet was on, what's going to happen is here you have north and this. So on the south, what's going to happen is, remember, opposite attract. So it's going to be attracted here and repelling here. So here you have attraction, and here you have repulsion. So here you attract, here you repel, and then all of a sudden here, it's going to get stuck. There's no reason to move on because here it's happy. North is going into south. Here's my magnetic field. There's no reason for this to move anymore, so it's getting stuck. So if you go back to the previous slide, if we go back to here, this is important because one part of it is on and one part of it is off. So if you design your thing correctly, when it's here, it's on. So here it's on. So when it's on, it's going to do what you want to do. It's going to attract here and repel here. Here you're going to have it off because as it rotates around, remember, only part of it was bare. So as it rotates, all of a sudden you're on that painted part of the wire. So it's going to be off. So here you have it off. So this, once it's off, there's no magnet. So it's just free to move. Here it's still off. So it's still off, so it's free to move. If it wasn't off, then what will happen is it might push it back this way. So what will happen is, you don't want a motor that goes a track off and then push it back. You want it to rotate in one direction, so you still want it off. Here, technically you want it a little bit more like right here before you turn it back on, But here it can be. So as it rotates around, so notice how it's rotating around. It's going in a clockwise, so rotation is this way, here's rotating this way, here's rotating this way, and then here's rotating this way. I kind of drew this one wrong, let me erase it. So you want it more like, slightly more like this. So if it was north and south, what's going to happen is these two, since it already has that momentum, it's going to push this way. This is going to attract this way. So what's going to happen is in the simple motor, just because it has one on and the rest off, it's going to continue moving around in a circle. Now, if you're watching enough of these videos, or if we did this in class, you'll notice that sometimes it requires a little flick in order to get it going. So if you go back to that video, you'll see initially it doesn't work until he kind of pushes it. And it's because it might have been in the off position, so it wouldn't have moved. Now, in most motors that we have, we kind of don't want that. We actually want something that has multiple things. So this is an example of simple motor that's really, really easy to make. But in reality, you want motors that are a little bit more complex. So the motors that we want to look at tomorrow is I want you to look at for your homework, has a little bit more than this. So here you only have one loop, but most motors that you have multiple loops, usually 3. But that's what I like you to read tonight for homework. All right, so hopefully that makes sense. Hang in there. Supposedly it's going to be a rough 2 weeks ahead of us. So be safe, stay at home, and take care of yourselves.